Hey guys, so this is your review for Math 3 for Module B, Exponential and Logarithmic Functions. Okay, so the test is going to assess you in 5 areas, all right? 5 sections. Number 1, analyzing exponential functions. Number 2, solving exponential equations. 3, understanding basic logarithms. 4, the logarithmic properties. And 5, analyzing the log function, bringing everything back together. Okay, so point number 1, you need to know how to analyze exponential functions, all right? And here are the 10 steps that we would use to analyze exponential functions. You do not have to have these memorized, but you do need to have knowledge of each one, all right? So we're gonna run through one together, all right? This is -3 times 2 to the x plus 3 minus 4. It's an exponential function, all right, that I've graphed on Desmos. As you can see, the function is upside down. This is due to the minus sign. Okay, so this would be the sketch. You need to have a kind of a rough idea of what it's going to look like even before you graph it. That way, in case you hit a button wrong in your calculator, you know that something's up. All right, so this has to be an upside down exponential function. Here's a table of values for you. All right, and we're going to evaluate a point. So let's say we were to evaluate f of 2. All right, that would mean we would substitute 2 into our exponent, which would make our exponent the 5th power. So we'd basically be raising 2 to the 5th power. I'm following order of operations. 2 to the 5th power is 32. Next, I multiply that 32 by that -3 to get -96. I subtract 4 and I get -100. And just to verify, my table has the point 2, -100. All right. You want to understand whether or not this function is a function of exponential growth or exponential decay. It's obviously when you first look at it, you know, it appears to be exponential growth, right? And even though the function values are growing in magnitude, this does not necessarily mean that the function is increasing, all right? This minus sign flips the entire function. So even though your outputs are growing in magnitude, they are decreasing, all right? So I gave you a little sentence right here. The exponential function has a base of 2, which signals exponential growth. The function has been flipped due to the negative, however, and is now decreasing rapidly. Okay, this has no x-intercept, and the y-intercept is 0, -28. You could find the y-intercept either by the table, or you could substitute 0 into your function, find f of 0. All right, no x-intercept. Well, most of these functions do not have an x-intercept. Your parent functions don't have x-intercepts. The only way that they will have is with a vertical transformations. However, this vertical transformation for a negative function just moves it further away from the x-axis. All right. Next thing, function is decreasing across its entire domain. The function is negative across its entire domain. Horizontal asymptote is -4. You can tell that very quickly by seeing the vertical shift right here. Domain's -infinity to +infinity. The range is bottom to top, -infinity to the top is -4, not including -4. Transformations are 3 units to the left, 4 units down, and it is flipped across the x-axis. All right, second very important point for this module was solving exponential equations. So, and of course, at any point, feel free to pause the video so that you can see, you can maybe work one of these problems out. As far as exponential equation goes, there's 2 types as far as I'm concerned. There are exponential equations that you can solve with a common base, and there's exponential equations that you can use logarithms to solve. In the test, I'm just going to give you exponential equations. It's up to you to decide a good strategy. All right, here's an example of when you would use a common base, right? I have 8 to the 6x minus 5 power times 2 to the 3x plus 1 power equals 2 to the x plus 9 power. And all that's base 2. So you always want to find that greatest common base. And even if you didn't find the greatest common base, if you just find a common base, you can still get this problem right. Okay, so feel free to go through those different steps. Okay, when would we use logarithms to solve an equation? Well, notice this one right here. Even though we could get a common base in a certain part of the problem, it might not be the best idea. So here I have 3 times 10 to the power of x plus 4 equals 3,000, and I want to think about cleaning this problem up a little bit before I apply any properties of exponents or of logarithms. So I'm going to divide both sides by 3 first. So I get 10 to the x plus 4 equals 1,000. All right. And yeah, you could change 1,000 to 10 to the third right here. Then you'd be setting 3 equal to x plus 4. And that's fine. All right. Now, if you know your logarithms, you know how to change this expression into logarithmic. So it's log of 1,000 equals x plus 4. That means 3 equals x plus 4 and x equals negative 1. Okay. We're running out of time here, so I'm going to go over the last 3 parts rather quickly. Basic logarithms. You got to understand how to form a logarithm. All right. Logs are the inverses of exponents. We understand logs because we understand exponents. For example, log base 3 of 9 is 2 because 3 squared is 9. Okay. Logarithms answer this basic question. What power of this base gives you the answer? For example, log of 1,000, we know that's 3 because the question was 10 to what power is 1,000? So in other words, the logarithm solves for a power. The outputs of the logarithm are powers. Okay, powers for their exponential counterpart. Okay, and if you understand this idea, you know now why logs have a table with many decimal outputs, et cetera, et cetera. All right. Please make sure that you're able to compare logs and exponents. Remember that their domain and range are flipped. While exponential functions have a horizontal asymptote, logarithmic functions have a vertical asymptote. All right. That they're pretty much similar in shape. They're inverses. Okay. Don't forget your log properties. There are 3 main log properties: the product property, quotient property, and power property. And feel free to go over this part. Is best if you go over the examples that we've done in class. I think I put another whole worksheet of examples here on the shared folder. So make sure you look over those. Okay. Make sure you know how to expand and also how to condense. Okay. And make sure you're not making these common errors. I see sometimes common errors for something like log of 3x to the 4th over 5. I have seen some students say this is log of 3x to the 4th divided by log of 5. Right? You want to remember if you're working with these to not get your properties mixed up. All right. So if there is division within the logarithm, this means you will have subtraction in your expanded version. Okay. And you want to take things step by step. This is where you want to remember to look at the structure of the expressions. Okay. Feel free to work out these problems on your own. The last thing is you need to make sure you can analyze the log function, all right? From the basic log function all the way to a transform log function. So we know log of x is a function with a vertical asymptote at 0 that is slowly, very slowly increasing. Why is it increasing so slowly? Because these outputs are the exponents, right? You want to think it would take an input of 100 for me to get an output of 2 because 10 squared is 2. 10 squared is 100, okay? You want to remember that there's a vertical asymptote at 0. In our transform version, there's a vertical asymptote at 3. So hopefully you can see that a certain part of the function gives you the vertical asymptote. All right? And think about it. Can I have the log of a negative number? Well, think of substituting any number less than 3 into this function, and you would see what I'm talking about. Okay? That's almost all of our time. The only other thing I can say, in behavior, well, as x approaches 3, my function approaches negative infinity. And as x approaches positive infinity, my y's approach positive infinity. Very slowly, but they approach positive infinity. All right. Remember, your domain here is restricted, just like your range was restricted for your exponential functions. So in the end, you see that it's all tied together. If you have any questions, let me know. Feel free to shoot me an email. And that is pretty much it. Okay. Peace.